All right. Hello, everyone. This is Keanu Crouch with the Cyber Defense and Countermeasures. We're here to do the cohort for lesson 3. Tonight, we're going to explain the important system and network architecture concepts. We're going to go through it and kind of just give an overarching breakdown of the concepts explained here. Any questions, please throw them in the chat. And then at the end of the recording, we'll make sure we are going over those at the end of it. Just a second, let me answer a question. Okay, so let's go ahead and jump into lesson 3. And with this, we'll begin with the lesson introduction about what we're going to be talking about. So the lesson objectives. Lesson objectives for this are we're going to know how to review system and network architecture concepts, explore important operating system concepts, review cloud deployment models, review identity and access management concepts, and review data protection tools and techniques. We're going to go ahead and just jump into the information. So this is just a short video that can kind of give you an explanation of what you're going to be learning in this lesson. Generally try not to play the videos on my videos just because I'd rather you watch that on your free time. We kind of want to get more into the content. So to start, we're going to explain the importance of system and network architecture concepts in security operations. We're going to talk about how system and network architecture assist in providing a more secure environment for our business and our processes, and how implementing these designs kind of from the ground up can kind of have us with a more secure, a secure infrastructure to work off of. And if you start with a good secure base, then essentially everything builds off of that. So you kind of apply security concepts within the full life cycle of your business processes. So we'll start with system hardening. System hardening is essentially doing your best to shorten or shrink the attack surface of an overall system application. A lot of this involves removing bloatware. Bloatware is considered things that come with a system as is brand new. Disabling features that may be prone to attack that you may not need. Essentially, when you're hardening a system, what you want to do in the actual operation environment is you want to identify the system that you need for your actual business objectives, and you want to basically create a golden image. So basically, that image has everything that you need in order to conduct business at your organization and removes everything else. So that's where it gets into this. It includes disabling unnecessary services. So essentially, you want to basically make a perfect image that allows your employees to do their business, and that's all that's going to be on there. Everything else can be removed in order to prevent an attacker from leveraging something. What this essentially does is create that golden image. You just basically clone that image, so that image should be the same image across the organization. There may be small tweaks made to it based off of where that user is sitting within the organization. Some users in some certain sections may need access to different software as different users, so maybe that golden image can be tied to a specific role. So for instance, let's say you have a finance department in your organization, they will have access to payroll systems. So that may be a service or an application on their systems, but that same service or application should not be present on to the human resources or research and development office, where they may have something like a research and development may have specific software that's designed to assist in code development, like Visual Studio, things of that nature. So essentially, you can kind of apply the use of separation of duties with how you actually set up your golden images. In the Department of Defense, they call this the secure host baseline, which is spread across all just about Department of Defense systems. It's basically Windows environment, Windows operating system, that's completely clean of everything that could possibly be leveraged for attack. And they start with that specific secure host baseline and pass it out to different organizations, and those organizations build off of that. But the pure baseline is basically just like a clean image with everything removed that may not be necessary. So they call those secure host baselines, and they apply. So you see here the DoD STIGs. STIG stands for Security Technical Implementation Guide. It's a step-by-step process for how they would implement those different security controls and how they remove certain things and um, change certain features in order to create the most secure setup. So they also have CIS benchmarks. These are used kind of more in the private sector. It's essentially the same idea, but it basically creates a just a guideline. So essentially, it starts with the guideline for how you want to secure your systems, and you kind of once you start at the bottom with a straight clean system, then you kind of can put an application on there. You can pen test that application while it's on that in that environment, and then kind of just build off of that. You put another application on there, you test it again, make sure everything works, and remove the things that you will not need. So we then get into Windows registry and file systems. So essentially, the Windows registry is like the brain of a computer. It's essentially it it tells the computer what to do for certain things. It has settings. Anytime you make a setting change on any Windows system, I can guarantee you if it's not, it's at least one registry key that's going to be changed. And essentially, a lot of times when they're doing these security implementations, the best way to do it is to just possibly, if you can, just jump into the Windows registry and then change those specific registry keys. This can also be done through group policy. So across the domain, you can change certain registry keys to prevent users from doing certain things, or they also be used to track. One other thing you can do with registry keys is if you have a USB and external storage policy in your organization, when you plug a USB, anything into a USB port on a computer, a registry key is set. And you take that out and you plug a different in, another registry key is set. So when you're kind of doing investigations, one of the things you can do is you can go in the registry and you can identify what type of device it is, the serial number, all of these things that you can use for your investigation. So if someone's like, "Oh no, I didn't plug anything in the computer," but they have a USB stick in their pocket, you get the serial number off of that, and it matches the serial number that was found in the registry on that system that they were working on. And there you go, right there. It's like it kind of just tells on you. You can actually set up certain PowerShell scripts to monitor registry keys. So as soon as something happens, you can basically make it so it shoots out an alert, and it's essentially just monitors the registry. Basically, it shoots the alert on, and it can basically say, "Hey, this system had something plugged in the USB, and this is the serial number." So you actually be able to be armed with that data. So when you go to the user's desk, you can say, "Hey, you got something plugged into your computer right now, and I can see it." So that's one of the ways that you can protect your network as far as monitoring. It's one of the ways that you can change different security controls within a system and based off of registry keys. So configuration files, um, because Linux does not have a registry, it uses configuration files. It's essentially the same thing. It basically is the instructions for how the computer operates. Um, these files can change how different apps run, how different programs do certain things, what users can do certain things, but the information in this is not in the same key value pair as a registry key. It's essentially like a document per se, and it's just so when you see these INI initialization files, extensible markup languages. So essentially, what will happen is if you actually look into want to see the configuration for a program, these file names, these file types, that's what they're actually called. So it'll be like the um, elastic.yaml file or filebeat.yaml file, and you go in there and you actually see how filebeat is actually configured on that Linux system. So when you look at these, it's going to be the file name dot and then whatever language is used to change the things in that file. And the reason for these is some programs actually only understand certain languages the way they're written. So some accept JSON, some accept YAML. So you don't have to be perfect on how to write specifically in YAML unless you become a security engineer and you begin to write these configuration files for your organization. And you have to get real smart on them. But as far as just as a cybersecurity analyst, you know what they are, and if you go in there and read them, a lot of times they read just like plain English. You can kind of see the specific settings, and it's not like kind of a C# based code. It's not something that's quite difficult to read. So then we get into system process. System process are things that are running background of your computer at all times. Um, these things can be something like the average user does not know about the system process in the background. One thing to note about system processes is because they are always running, and like you can click something on your system and it triggers a background process that the user will never see. It is an actual vector that attackers will use if they can link their malware to a specific system process. It could be something as simple as you clicking Google Chrome on your system. Certain processes kick off in the background, but that process might trigger a piece of malware. So that's kind of a logic-based approach for how attackers can leverage systems. So one of the ways you actually can monitor this is within your SIEM, you can have logs, like Windows event logs. As soon as a new process is kicked off, it's going to have a specific event code that is shot through to the SIEM, and you can monitor your SIEM. So if you see like a weird process name, or if you see if you only know one instance of a process running and two of them pops up, yeah, you can further investigate. So essentially, if you have an organization where everybody kind of does the same thing or very similar things, everybody should kind of have the same system processes running. So you can identify anomalies through what's called long tail analysis, um, based off of just kind of this is not like this, this is not like that. So essentially, applying the use of long tail analysis is if you have 70 instances of a process running and you have 70 systems, then that process is probably normal. But you have 70 systems and one process is not like the other, then that may cause you to do some investigation as to why that is not like the other systems. So hardware architecture talks about the underlying architecture on a system. It's like when we talk about ARM and x86 architectures, is basically it's used to it's certain programs are they need certain architectures, basically the way they were built to run, and it leverages architectures in order to run efficiently. And a lot of times programs are not built to be interchangeably through certain types of architecture. So something that runs on x86 may not run on ARM. That's one of the things that you may want to look into when you're purchasing software, purchasing things, using your organization. If you have a pure ARM based architecture, which is not common, and you buy something that is not running ARM, then essentially it would not work unless you use what's called an emulator. So basically, you can run an emulator within like an x86 architecture that basically tricks the software, the program into thinking that it is ARM. You can run an ARM emulator, and essentially that's generally used for if you have a piece of software or something that is ARM based and you're not about to change out all of your systems for this piece of software, but you need it to run, then you can run an emulator in order to just have that one purpose built program run for your business functions. So we're going to get into virtualization. This is important because virtualization is becoming the new hotness. It's got a lot of benefits. One of them being you can kind of spin things up a lot faster. Things are a lot more resilient as far as running on your network. You don't instead of having like one server that is a dedicated server and is running purely off of what we call the metal of that server, whatever system process you have, whatever that server is used for. You can essentially virtualization software on that same server, and let's say we can run four servers off of that one server. So we can leverage our same architecture and but get more usability out of it. So we can save money like this. We have better control over it. And once we get into emulation and stuff, we can identify ways for us to have more capability because we might have one specific type of server where a program may not be able to run on that specific type of server. You can apply virtualization to allow that program to run and kind of trick it into thinking it's running on the proper metal. So within virtualization, we have hypervisors. Hypervisors are type 1 and type 2. Generally, type 1 hypervisors are used in enterprise settings. One of the reason that there's a lot less overhead on type 1 hypervisors, those are the kind of networks where you have server center with a bunch of server stacks and you just have a lot of stuff going on. Like it's just everything going on. So you want to minimize as much processing overhead as possible. So you remove the operating system and it's basically the metal, the hypervisor, then whatever application or container that you're running on top of it. We're going to get into a diagram about this in a moment. Type 2 hypervisors are essentially what you're going to be running a lot of times in your home labs. Like for instance, VMware is a type 2 hypervisor. So when someone's running a bunch of VMs or they're using VMware ESXi, that's a program within your operating system. So if I was to download VMware Workstation Pro on this computer and run VMs out of that VMware Workstation Pro, that would be considered a type 2 hypervisor because I'm using the operating system. So this would be considered a type 2 hypervisor, this diagram. So the hardware is the system, and then you're running. So let's say the operating system is Windows 10, and then the hypervisor will be VMware ESXi, and then these are the different operating systems within that. So you're still using some type of containerization, but if you think about if you're trying to go for efficiency, you're doing things with, let's say you're in your Windows XP trying to run an attack on your Windows 7, and it's going to take a lot of RAM, it's going to take a lot of load off of your system. You have to think of how much processing power is being used to run this operating system and this hypervisor within that operating system, and then this process you have going on here that can take a lot out of the system. It's very taxing. So essentially what you would want to do in an environment that you're going to be running a lot of different VMs, different containers, you will want to remove this operating system and just have the hypervisor sit on top of the hardware and run the containers or the operating systems outside of that in order to remove the computational overhead of running an operating system. So we have application virtualization and containers. So the best way to kind of look at this is the graphic here. So as I was talking about with how you actually have your type 1 and type 2 hypervisors, containerization can be applied in a way for you to remove the overhead of a guest operating system that which feeds your binaries and libraries that run your applications. So if we go back to our it's in kind of software development, you know that applications when they run, they don't have all of the resources they need to actually run. But what they do is one of the reasons why when you're downloading software, it asks you what operating system you're running, and you have to download software based on that specific operating system because when they create the application, it's going to be reaching out on your system to look for different binaries and libraries, which are found in a standard operating system. So what actually happens in this type of containerized environment outside of what we're commonly known as kind of a standard operation, a standard type 2 hypervisor, is you specifically give the binaries and libraries that the application needs. That's it. So one of the uses is Docker. Docker is a very common virtualization software, containerization software, should I say. But essentially, instead of if we remove this guest operating system and we just give the application the specific binaries and libraries it needs to run, we can get the use out of the application, but remove this overhead. And essentially, and that's what containerization it allows us to do, is to maintain efficiency while still getting the job done and actually increase efficiency by being able to have more applications running on the same base server because we're removing a lot of this overhead. So from a cybersecurity analyst perspective, one of the things I want to bring up from blue team, red team type of defense mechanism, the two things you should think about. One of them is there are attacks out in the world where attackers can hop between virtual machines and attack different applications. So the way they're doing that is if an attacker gains access to this host operating system, then essentially all this hypervisor is a program running on the host operating system. So if they gain access to the host operating system and it's like kind of an admin privilege, once they gain access to this, everything from this hypervisor line up, they can do whatever they need to do in order to uh, conduct their actions on objectives. The same thing applies here, but the attack surface is reduced because you're not running all of this extra stuff. So essentially, if you have a secure host baseline that we talked about, a host operating system, that attack surface is reduced. You reduce and there's nothing else that the attack can gain leverage to. You're reducing the attack surface on your whole containerization implementation. One other thing to think about when we're talking about securing networks and things attackers like to leverage is one of the things that kind of propagates on both of these is these binaries and libraries. One thing attackers like to do is you can inject code into these specific binaries and libraries that when the application calls out for that binary, it executes, it could be actually executing malicious code. So one of the things is monitor for any type of interaction with a binary or library, which will be identified within the registry key, or it can be identified within an event log. So if you see weird activity and then you see the activity mess with binaries or libraries, and one of the ways you can do it on Windows systems, if you look for any type of odd software um, writing to or creating .dll files. .dlls are called dynamic link libraries. Those are libraries that programs call out to that are found on standard Windows systems. So those are just two things, food for thought from a cybersecurity analyst perspective, because a lot of the reasons why you learn a lot of this information is you have to know how it works, and then once you know how it all works and why it's all used, you kind of have to think of from a perspective of an attacker and what could they leverage to attack it. So that you have to think from a perspective of an attacker, and that's how you're able to protect against attacks. So understand how it works. Understand how it works, and you can actually find ways to attack it. Once you find ways to attack it, you implement controls to defend it. So now we're going to get into cloud deployment models. This is pretty simple. Cloud deployment models, public cloud. We'll start with what a cloud deployment model is. Cloud deployment model is how your organization is leveraging the cloud and how it is implementing that concept into its business processes. Public cloud, the best way to look at it is when you start up an Amazon AWS instance and you are running this instance is running on a piece of hardware that you have no idea what it is. You're basically putting all your data out there. You're kind of starting up. You're going to the AWS website. Now you can start up VMs. You can start up applications. You can have that stuff run. That's going to be the public cloud. The private cloud, you can actually get this hardware, and they can basically give you dedicated hardware, but it can be accessed over AWS's infrastructure. But it's still your organization's hardware. It is quite expensive because you still have to purchase that hardware. They're just running their um, software and their infrastructure over that hardware, but it is still dedicated only to you. Use a hybrid cloud is when using both of those. That's all it is, using private cloud and public cloud infrastructure. One of the reasons why this is important is because the introduction of all of this cloud technology that we're seeing across everything. Everything uses AWS, everything uses Azure, everything uses Google Cloud Compute. With that, when you're using a public cloud instance, let's say you are using something, you're using that for some type of proprietary information. One of the things that has come up is when that data is on the public cloud, do other organizations have access to it? You don't own it anymore. At that point, you're basically giving it to AWS, and it's not in your purview anymore. So a lot of organizations will have their business functions where their customer facing business functions will be on the public cloud, but their actual proprietary data and research and development information and very sensitive information will be held in the private cloud. So that's an instance where you'll see a hybrid model implemented. That's kind of the reason for the separation of them. All right, so serverless computing and software-defined networking. So serverless computing, it's kind of hard to understand at first, but until you kind of see it, in action, then it's essentially, imagine computing functions, but there's no physical server that's running these computing functions. So think of a server that like a file server or a web server or something that is in any type of server, identity access management. It's got a specific function. So when you're interacting with the server, when you're pulling data from the server, you're pushing data to the server, it's storing that data and it's giving you an output. Serverless computing, imagine if instead of that server getting the same function and use out of it, but it's all just like code and like software. So essentially, when you if you want to log into something or if you want to conduct a transaction in your web server, serverless computing will conduct the transaction and give you the outputs that you want, but there's no actual server. It's basically taking in the data and then conducting functions on that data and spitting out the response that it wants and putting the results of it somewhere else. But it's not specifically a server. It's just running functioning code at all times. It's like almost like a pipeline, like it ingests an input, it runs a function on that input, and it gives an output based off of um, what the organization kind of what their actual business process is. So with that, there are risks with serverless computing in that it does not have a specific server, a physical server that it's running off of. And when you don't have a physical server it's running off of, everything kind of just happens essentially, if I must say, in the ether. It all happens in the ether. So if something occurs where, let's say, your function is not working properly or something starts to fail, you can't go to like a server room and reset a physical server. So incident response, disaster recovery, all of this is literally virtualized and it's a function. So you actually have to kind of get down to the weeds to figure out why the function is not working properly. And it takes a lot more expertise and understanding of the overarching infrastructure in order to address the issue. Um, like the best way to look at it is here it says use application logic to process the action. So it's purely in the ether and it's all logic based. So when things happen, it's not like you can have functions give out logs, but it's not the same way as actually having a server do functions and you have like proxy server logs. It's not the same thing. It's like it's purely virtualized and it's kind of like throwing data into the ether and it gives you back a response. Now we get into software defined networking. So the best way to look at software defined networking, well, the reasons why you want to use software defined networking is because it allows you to segment your network in the same way that you would in an actual data center, but through a virtual model. So you can actually do all of these through just commands, and it's the same exact functions, but it's not actually on like a physical Cisco router or a physical Cisco switch. It's all separate. It's all virtualized. So the best way to look at this um, is this here. So we'll start with control plane. Makes decisions about how traffic should be prioritized and secured and where it should be switched. So when you think of control plane, think of this is the brain of software defined networking. This is the data needs to go somewhere and needs to know where it's going. What is actually controlling? What is the brain of the whole operation? The data plane takes control in the same way as a switch would actually run traffic. It actually moves the traffic where it needs to be based off of instruction given it to by the plane. The management plane is essentially where your network administrators would sit. It's where the actual traffic is going to as far as um, if it's going across, if you're just like a point where the traffic is going across, if you're just a data center, it just depends on the use case. But the best way to understand it is if we think of the control plane, think of this as the brain. This has the instructions for how the data is actually going to be going across the network. It tells the data plane and the devices, and think all this is virtualized. It tells the virtualized devices what to do with the data that it gets, what traffic can go through it, what traffic it needs to block. So essentially, it's still the same idea in terms of physical networks. It's just all in a virtualized environment controlled by planes versus like if you want to block certain traffic at a certain point in a network, you would actually have to physically either go to that firewall or go to or remote into that firewall, depending on if your organization allows that, or you would have to go to the routers, set access control list. With a software defined network, you can run it through a specific software. You can basically log into a page and it would basically run as a program, and that's how you actually run your network. You can, so essentially a lot of work from home jobs when it comes to network administration, especially when there's a software defined network, these are the types of systems that would basically allow that. You can basically sit at home and be a network administrator because everything is virtualized anyway. That's the best way to kind of explain software defined networking. I know a lot of students can read too far into it and don't take away that it's essentially just a virtualized approach to the physical infrastructure that's already in place at most organizations. Zero trust. So you'll start to see this more, especially when we have organizations that have a lot of partners. As technology evolves, the attacker is evolving too. So essentially, zero trust, exactly what the name says, like the don't trust anything. Re-authenticate. Like basically, authorizations to certain resources, should recheck it. That's one of the things that you'll notice when we kind of start to see zero trust creeping into our standard business practices is when you're at work or something and you get annoyed because every time you click on something it asks for your password again. You switch from one system to another, it asks for your password again, and you're like, this is really annoying. It's zero trust. It's like keep checking the authentication, especially when you're going from one website to basically, let's say we have a third party website that we use for our organization, going to ask for that password. It's going to ask you to log in again because even though those are two part of your business processes, zero trust means they don't trust each other. They don't trust the credentials that you've already logged in with. So the reason why zero trust is becoming a thing is because of how we're starting to work as a society. More cloud is being identified. More remote workers are being hired. After COVID, we had to identify a way to get the job done, but we had to physically separate. We did that. We identified the idea that increases our attack surface. How do we stop that? Start implementing zero trust in our organizations. Mobile devices. A lot of organizations allow you to use your mobile device, but still allow you to access resources, and they still want it to be secure as if you were actually on the physical network. Outsourcing and contracting. This is a really big one. So it happens in the government. It happens if you look at different attacks that happen in the private sector. One of the ways that a lot of organizations get attacked is not because they attack the specific organization, they attack the contractor the organization leveraged to do a specific function for them. So you get into the contractor has access to their network, but there's no zero trust architecture in place. So basically, the same credentials will work on one as they work on the other, and they just move straight over. So you could put all the security controls in places you want. As soon as you give access to a third party contractor so they can do a task for you, and they may not care as much about security as you, they just want to do the task for you and make as much money as possible. They leave their things insecure, and then that gets attacked, and now they have access into your organization's resources. Same thing with wireless networks. Wireless networks, it's hard to control because it's airwaves over there. So with wireless networks, wireless frequencies, if that can be picked up somewhere, if you can pick up the frequency and you can interact with the access point, there's no security. You're part of the network now. But there's zero trust architecture, there's zero trust concepts in place on the network, zero trust controls, then it's not even going to let your device connect to it. It shouldn't. But you can't really control wireless networks as we control wired networks because wired networks, you have to have physical access to an Ethernet cable somewhere or Ethernet plug, or you have to have physical access to something where wireless networks, you can just be sitting in a creepy van out in the parking lot. And as long as you can see that signal, you can connect to that network. So when we get into some of the increased benefits of zero trust architecture, it gives us greater security. That's the point of it. That is what we actually want to be able to do. We want to secure our networks better, but still get our business processes done in a decentralized environment. We also have better access controls. We can get more granularly. So when better access controls have links with the increased granularity, we can specifically be very stringent on what certain users have access to because everything has its own security architecture, everything has its own identity access management. So with that, if I don't want you to log in this specific resource, then when you try to click over and just try to go into it and think that your credentials are going to carry over, they're just not. Like it's because you don't have access to that specific resource. Improve governance and compliance. With that, you have a greater control over what users are able to do. So especially when we talk about HIPAA and healthcare, certain users should not have access to certain things. With zero trust, they just wouldn't. Like they wouldn't be like a leakage where or a spillage where someone can have access to something they shouldn't have access to, and they just jump into it because with zero trust, you have to specifically be given access to that resource versus your credentials just work across the network and they just hope you don't try to access certain resources. So, in order to properly implement zero trust architecture, you should all have an understanding of the essential components. These are essential components that kind of propagate across most things in cybersecurity and information technology. Endpoint security, identity access management, policy, group policies, cloud security, what you can see on your network, who is separated, who can talk to who on the network, how to best protect the data, if it's encrypted, if it's not, um, threat detection through your logging and your security operations centers. So with that, you it does not identify security through the boundary. So in order to actually access certain things, if you draw a circle around all of your resources, zero trust is talking about point to point access. What if we want to also ensure that we're protecting the boundary around it so you're not even getting to the first point if you don't go through certain I guess perimeter, certain borders, and that's where security access service edge, secure access service edge comes in. It uses virtualized environments to actually control who has access to the overarching wide area or local area network, essentially wide area networks where you're talking about remote and decentralized work. So it is actually, if you draw a circle around it, how are you actually getting to that circle? And the best way to do that is secure access service edge. Essentially, the best way it does that it applies a defense in depth, kind of like a stacked approach to it. So there are multiple different things involved in SACE that essentially ensure that users are not able to gain access, and if they do kind of circumvent a control, there's something else coming right behind it to actually prevent them from gaining access to the overarching wide area network. So that was topic 3B. No, that was topic 3 alpha. Now we're going into topic 3 Bravo, which is exploring identity and access management. So authentication factors. This is a big one. Two-factor authentication. Um, you know the ways that we're actually authenticated is something you know, which is your password, something you have can be like an access card. In the government, they use common access cards or tokens. Something you are, those are generally biometric. Biometrics are not found commonly because of the failure rate in them. And kind of like one of the things that can occur is, for instance, retina scans. One of the things identified out in the practice of biometrics is when women are pregnant, um, something changes within their eye. So retina scans will not work because it or the something about like the structure or something about their eyes change when they actually are pregnant and can't get in anymore. Um, and just based off of just like even your scanners can get really good, but it could like just based off maybe you have a specific oil on your finger. Our bodies naturally produce oils and stuff. They just don't work as well as other factors. But and they also are very very expensive to implement. So normally you would not see this out in the wild unless you have an organization with a lot of money. And there's generally a way to kind of override it just because of the failure rate within biometrics. It has to be implemented very well, and it still has a high chance of failing. Two-factor authentication, we all know what that is. That's where You try to log into something, we have a Duo on our phones. You have to or send you a pin through an email, something. So I can enter my username and password, and it's like I know this stuff, but then to make sure it's really me, contact me on another resource that I should have access to in order to ensure it's the person that you think it is. So these are the kind of the common ways. This is essentially what Duo does. It's you have the different choices. So this is basically how it does a two-step verification. There are some systems that have just pure passwordless authentication. So when you try to log in, you just basically put your username in and it just pops out a notification on your phone to tell you that you or to see if you're actually able to gain access. So with identity access management, you also have single sign-on, single sign-in. You access one system. If you can access that one system, you can access other systems. That's basically the way it actually is designed to work. The downside about it is if someone gains access to your credentials from that one system that you access, then they also have power to access the other systems that that same single sign-on had access to. One of the ways that they prevent against this or have controls against is using single sign-on with multi-factor authentication. So they still get the same security controls from multi-factor authentication. With single sign-on, it actually adds efficiency in the work. You don't have to keep logging in. So combining those two will allow users to be still be quite as efficient with the same security in place. So privileged access management, if you want to think of it from a perspective of ensuring that even if a user's credentials get taken, that the attacker does not automatically just have the keys of the kingdom because he took those credentials. They still have certain privileges, and those privileges. So if you monitor it, it's basically say like, okay, this user does not have access to this. Why is he even trying to access this? And they may be able to assist in identifying if someone's credentials are taken. So you ensure that just because a user has credentials to the network, are they accessing specific resources that they do not have access to? So it's like an audit policy. It's an audit program that identifies when users are doing things they shouldn't be doing, and it alerts or sometimes blocks. It depends on the policy that you have set up. So federated trust methods. These are ways to actually ensure efficiency, so users do not have to keep logging in by kind of using a way for the access to propagate across multiple different iterations. A federation is just essentially like organizations that have all agreed to work together and accept credentials, accept the same set of credentials, so you can access multiple different resources. One of the ways we can kind of see this is that I'm pretty sure like Instagram and Facebook are a part of a federation. Like you can, as long as you have the credentials in one, you can log into the other, and you can like it's how you can like post to one and then automatically sends the post to the other because the credentials are it's a federation. OpenID. Imagine it being a third-party security broker. So imagine it being you have two different entities. Let's say you have Bank of America and I know the IRS, and they work together. They do business together, but they want to be able to have users use the same credentials to get in both of them. Then essentially, imagine them moving that over to a third party. So when you put in credentials, it takes those credentials and sends it over to that third party, which would be running whatever OpenID iteration or implementation they're using, and then that third party will come back and say yes or no. So basically, they only trust access to their resources if that third party says yes or no, and that third party can also have certain things in place where it has its own multi-factor authentication, but it essentially allows organizations to work together as far as letting users utilize credentials, but also protect their networks from being attacked by kind of pushing that over to someone else that may have more resources and more capability to be able to solely focus on um, securing the network or securing identity access management. So Shibboleth is a federated identity method. So it kind of works in the same way as a federation. It uses SAML, security asset markup language. Um, in order to actually allow organizations to talk back and forth. So reason I jumped straight down to Shibboleth instead of going to security access markup language, because you're going to see Shibboleth more often than you're actually going to see SAML like in a URL. Um, you're if a lot of institutions, universities and institutions use Shibboleth. So when you see this, just understand it's going to use security asset markup language. So security access markup language is essentially it uses tokens. So certain tokens are trusted by organizations and third parties in order to gain access to their networks. And those tokens can be written either XML or attestations are written in XML. So it's basically an attestation. Keep messing this word up. Attestation is essentially what is actually saying yes and no. So the actual granting or denying of access is basically written in the security assertion markup language, and it uses HTTP and HTTPS in order to have that to be the vehicle for that communication back and forth and determine whether or not, based off of the token, can that access be actually granted. So with Shibboleth, it just within the actual URL query, when you're going back and forth, the actual token is actually within your URL query. So you'll notice that when you're going to different websites within a Shibboleth implementation, if you look at that URL, it will be crazy long. And that's essentially your SAML token going across. So transitive trust. Transitive trust defines a relationship between authentication services. So essentially it says if you trust them, I trust them. And that's essentially organizations have to have some type of agreement for transitive trust. And most implementations, transitive trust, it's in industries where organizations work really close together and they have to access um, the same systems, but just in different networks. So basically, like you might work for one company that is a subsidiary of another company. In those types of instances, you'll run into transitive trust, where instead of creating their own separate um, security controls and security and domains for security, they basically say like, okay, we have all these employees. I'm a subsidiary under you. Whoever you trust, I trust. So I don't have to actually have the users go through this whole gambit and they were already on your network and they're already an employee of you. So cloud access security brokers. So essentially security, the perimeter for cloud resources. That's the best way to look at it. It allows you to control access and control activity to cloud resources. It's basically, think of it like your firewall for your cloud. Um, Different implementations of CASBs are forward proxies, reverse proxies, and APIs. Um, so your forward proxies, the best way to actually look at how your forward proxies work is to think of when you're using a organizational system. Like if you're using a like if you're like for instance, this laptop I'm using right now is a WGU laptop. So this is going to be using a forward proxy. So a lot of the resources that we use are on the cloud, and because it's a WGU laptop, a lot of the traffic is going directly to where WGU wants to do, and they actually have these devices configured in order to um, basically ensure that I'm accessing the resources and everything that's going across is safe. Reverse proxies are if I was to try to use my personal laptop to access the same resources within the WGU cloud. And at that point, they don't have the same controls over the system. And if I still am able to access it, I'm still kind of technically a part of that. I'm still kind of technically authenticating with that cloud access security broker, but I don't have agents and things running on my system as I would on my WGU laptop. Like for instance, if I want to set up a VPN tunnel separate from what WGU has set up on this WGU laptop, it will not let you do it. and it's because of the policies they put in place on the laptop. On your own computer, you can do whatever you want to do. That's why a lot of times reverse proxies are not what's used in organizational implementations, just because of the fact that users can't do that. They can find ways to circumvent the security controls in place. So you have APIs. So APIs are specific use cases. So basically, so an API called Application Program Interface, it would allow you to basically access the cloud infrastructure and do certain requests, certain calls. It'll allow you to do it. And if it's not that specific call, it won't let you do it. So basically, if your account is if you're using an API implementation and your account's disabled, then that's just what it is. It doesn't matter if you're going through a certain VPN, or if you're not doing the request the proper way, if your credentials are not sent over the proper way, it will just not even allow you to do it. APIs are used in a lot of different organizations, and it's a way for organizations to talk back and forth with each other without actually giving a third party organization access to their network. So like if you ever are trying to register for something, like let's say if you ever heard of ID.me, that's where you can get like discounts on goods and services because of your affiliation with some type of organization, such as the DoD, or if you're a cop or you're a teacher, you can use ID.me to access those discounts and those perks. So what it essentially will do is the resource that you're trying to buy or something, that the organization you're trying to buy something from, we'll just do an API called ID.me with that data, and ID.me will come back and say yes or no if this person is within their database and is who they want to be. If the organization asks for something else, the ID.me website's not going to do anything. It's not going to give them what they want. It's going to block it. So it's like a way for them to have a look-see into your databases and your servers and your information within your organization, only for very specific things, for very specific reasons, and that's it. So up to 3B, now we're going to go into maintaining operational visibility. So data loss prevention concepts. So how do we prevent data from being removed off of our network and off of our systems? This is kind of very high level as far as going down in the weeds. DLP can get very, very confusing, especially when you're trying to configure it. But essentially, if we break it down into policy server, endpoint agents, and network agents, the policy server says what is and what is not sensitive data. It is the brains, it's the computer. That is the person that says this is something that you all are not going to be allowed to do weird stuff with. You're not allowed to download. You're not allowed to take pictures of or whatnot, or take screenshots of. Endpoint agents are what's actually on the host that monitors what you're accessing and what you're trying to do with it. Network agents, the best way to see how a network agent kind of works is if you're in an organization that doesn't allow you to send PI across the organization email, put 123-45-678-9, just put it in an email and try to send it across the network. If you get a response back, that is the DLP working at the network response. It is basically looking for a specific string that looks like a social security number, and it will catch that across the network. That's basically how DLP works from the different points in the architecture or the infrastructure that you can actually see. Depending on how your organization treats it, I don't advise it if you have a strict organization, if you're just saying you're just trying something out, but that's essentially how to identify if there's DLP within an organizational structure. So when we talk about endpoint DLP, as far as how we actually monitor it, so when this information is getting sent, like let's say you're on a computer and you're putting something on a USB stick, or you're doing actions that look like you may be stealing sensitive information, there's specific remediation actions that the system can take, and the endpoint agent that is on the box can take in order to prevent you from doing that or alert the security team that you're doing that. Alert only is just saying like, hey, Joseph just touched something that he shouldn't have touched, or he just took a screenshot of something, or he just sent something in his personal email that he probably shouldn't have sent. But it's not going to do anything. It's just going to say, hey, this person just did something. Block it when you try to put something like, let's say you have Outlook on your work computer, but you log into your Gmail and you try to upload a file to send over, and you get an error that says like, you cannot upload this file to Google Chrome in this system. It's looking specifically at the file, it's scanning and saying like, okay, this file should not be getting uploaded into Google Chrome because Outlook is the only, I guess, prescribed application that is allowed to do these certain actions. Quarantine, so it basically denies the user. It might encrypt it, so there's like, as soon as it sees you doing it, it'll just lock the file down, so you can't do anything with it anyway. Sleep quarantines are also um, associated with alerts. So it'll quarantine it. You can't do anything with it. It might just encrypt it, and then it'll tell the administrator like, "Hey, you just try to do something," so it can kind of trigger something. So Tombstone is essentially a way to actually tell you what you did wrong and remove the actual file itself. If you want to test out Tombstone, one of the ways you can do that is if you get on your Gmail account and you try to send a 7-zip file to yourself. It's a file with the file extension of dot 7-zip. I'm pretty sure it's just dot 7-zip. Gmail will not let you do it. So what will happen is you'll send the file, an email. The user on the other end will get the file. Will get an email from you with a notepad error that basically says like, "Hey, somebody tried to send you something. We removed this. We're just letting you know that someone tried to send something unauthorized." So that's when we can actually see Tombstone in real life without actually causing any policy violations in your organization. So some of the examples of DLP print blocking. This is basically where I've actually seen this in person where the print server can tell if you're trying to print something that you shouldn't be printing, and it will let you print it. Some organizations they will let you print it, and the page will come out blank with it with basically like "C administrator," and they'll basically get an alert or a log. Blocking the use of external media. We go back to what I was talking about, the registry keys. When you plug in a registry key to something, you plug in a USB key, and it changes that registry key value. Some organizations will have it. So as soon as that happens, it basically will alert someone or it'll block use of the USB or it won't let you put things on a USB. They can do that through the file system or group policy. Some more strict organizations will legitimately either remove the USB out of the actual board of the computer. So there's a slot, but there's just nothing in there. So you can't put USBs in there at all. So we'll go into the BIOS and just turn off the USBs and then lock down the BIOS to password. Just trying to prevent the use of external media altogether. RDP is something that it is used to interact with computers. DLP can block it, but as kind of a security best practice, I always recommend students to when they get in their organizations, unless it is an organizational practice that their business requires them to do, like there is no alternative. Do not use RDP unless you really have to. The reason being is because when you log into a system through RDP, one of the very well-known attacks is Mimikatz. If you log into a system with RDP, it caches the credentials that you logged in with. Mimikatz dumps credentials out of memory. So all you need, so basically, if you have Mimikatz already on a system, all you do is have somebody log into that box through RDP, and you have their username and password. That's why Mimikatz was so successful. Um, for privacy controls, we see those a lot when we're kind of trying to copy and paste things from like I know my WGU computer will do it like when I'm trying to go from like Word to Outlook or Outlook to Word. It'll basically say like, "Are you sure you want to copy from this program?" This program is basically just kind of it just throws you an alert like, "Are you sure you can do it?" But sometimes it just won't even let you do it at all. Like you cannot. The clipboard knows what programs you're trying to copy from, and then it will not let you paste into something else. Um, VDI implementation. So a lot of VDI implementations, it's basically you have like a KVM and you log into the system that you're trying to use. And data from one virtual desktop interface cannot go to another one. And you can't, like a lot of VDI infrastructure, you don't even have access to the physical system. It's somewhere in a server room somewhere. So you are there to literally just work. So you can't take stuff from one thing to another. They use that a lot in governments, where they use secret or top secret classifications, and they don't want to worry about like any leakage. You can't copy and paste from top secret to secret or secret to unclass. And a lot of times they use VDIs to do this, whereas the point when you click it on a KVM, you are completely on a whole different physical system, and that physical system is not at your desk, it's somewhere else. Um, so then we also have data classification blocking. So you tag data with kind of what classification is. Some organizations will use this for blocking removal of PI. So they classify the data as PI, and then when data classified as PIA is accessed or that resource is used, it has certain mechanisms in place to monitor what's being used and block the usage of it. So these are different data types when it comes to DLP, kind of like what organizations want to protect. These are pretty self-explanatory. We have PI, health, financial, card holder data. Um, Financial and card holder data are very similar essentially, but to not get them confused, think of financial data as financial history about an individual, whereas cardholder data is something that you can actually use to process a transaction. So financial history, cardholder data, buy things, and then intellectual property, and this is identified generally through proprietary or organization proprietary information, copyrighted information, patents, things of that nature. So the role of PKI, PKI essentially is used for non-repudiation, and it's used to, like, for instance, if you're trying to send emails, that's mostly where it's identified using PKI to, you have a public key, you have a private key. You can tell where the data is coming from or where the email is coming from based off of using the user's public key to the user encrypts the data with their private key. You use the user's public key, it decrypts the data. If it does not decrypt the data, then that's not the user. If it does decrypt the data, then there's no repudiation. They can't say it wasn't them. Secure socket layer, it's basically 443 traffic, HTTPS, any traffic that is when you go on the internet, like for instance, this page right here is using secure sockets layer. One of the ways you can identify it is if you look in whenever website you're actually accessing, look in the top left corner, you'll see that lock. If you're on a website and you don't think you should be entering your card data on it, I do not recommend to do anything sensitive on any website that it does not have that lock in the top left corner. It means you may be over HTTP, which means it's in clear text. So anything you enter can be eavesdropped and that information be stolen. So logging concepts. So when we're talking about ingesting data into a SIEM, this is how we are able to see what's going on in our network as a cybersecurity analyst. So it collects logs from multiple sources. Think of getting Windows log events, packet captures, syslog events, all these different things into one centralized environment that we can actually look at everything and correlate events. So we see attack happening on a computer, we might want to go to, or we see something suspicious on a computer, we might want to go to our network logs and identify what box is talking to that computer. What is that IP address coming from? We might want to look at authentication logs to see, okay, did they authenticate as a user to this machine? So that's how we actually correlate all of our data. Our syslog data comes from our systems, like our routers, network appliances, things of that nature that has syslog. So let's say someone logs into a router, does something weird, and logs out of it. It didn't log into a host, so it's not going to come up as a Windows event log, but it will be a syslog, which will be logged into the same um, interface. So this will be using Elastic. You have Splunk as well. These are just implementation organizations can use to correlate all their data. And a cybersecurity analyst, this screens like this is kind of what you're going to be seeing every day. You're going to be looking at some type of dashboard that has all of the event information, and it allows you to click through certain logs, certain event types, certain alerts, and actually kind of try to put together a picture. So an incident response, you're going to be sitting in a SOC, and you're going to be looking at your SIEM. So essentially, your security information event management. This is kind of what a SIEM would look like from a perspective of a security analyst. This makes it look really flashy, in my opinion. A lot of times you're looking at it's not as pretty and it's not as flashy, but the information's still there. What I've noticed a lot is you'll see out in the field is they'll have all these flashy colors and all the other stuff, and it doesn't really tell you what you want to know. So you have to actually start clicking through stuff and looking at the raw log to try to figure out what it's actually trying to tell you. So when it comes to logs, make sure your time is synchronized, especially when you're sending in reports. If you say something happened at 6:43, but because your system's time was off, um, you told them 6:43, but really um, the time zone of the organization you're working in is actually the attack happened at 12:43. So when other entities are looking at or investigating your stuff, they're looking 6 hours. Or they're looking like at a whole different time frame. So it'll slow the investigation down, and it makes event correlation really hard if everybody's not on the same time. So logging levels are used to identify what is of importance. So the importance of a log message, and then you have your response. So a lot of organizations will correlate these different log levels to what you should be doing as a cybersecurity analyst based off of how their SIEM is set up. So you might go to an organization where they're like investigate all warnings. Might go to an organization where they're just like, if it's a warning, send it to the tier 1 guys and keep just send it somewhere else and just keep looking. Criticals you might have to go directly into incident response if you get a critical. So you might have to say like, okay, if you get a critical, do like a quick 10-minute investigation on it just to make sure there's a chance it's probably true and it's not just an error. If it's an error, send it to the security engineers that can actually prevent that from popping up again. If it's not, it might go straight into criticals, or they might completely just disable debugs. It might just say this happened too much. Just don't even tell me if there's a debug. So it depends on organizational policies and how they actually look at their how they want to respond to certain security incidents, and how well their SIEM is tailored as well. Um, this log, what I was talking about, the network appliances, they use logging levels to determine um, the same thing as far as how you should actually approach it. Those logging levels and how you should actually respond to them is once again something that's going to be set by your organization based off of best practices and their standard operating procedures. So here we just have a summary of lesson 3 and things we went over. Um, we're going to go ahead and end the recording so we can jump into questions.